Hi, today we will discuss moment area theorems. As an overview, we have the people behind the moment area theorems, then the theorem 1 and theorem 2 procedure for analysis and examples in using the more moment area theorems. The initial ideas of the two moment area theorems were developed by Otto Mohr. He is a German civil engineer and later stated formally by Charles E. Griff, which is an American civil engineer in 1873. These theorems provide a semi-graphical technique for developing the slope and deflection at a specific point on a beam due to bending. They are particularly advantageous when used to solve problems involving beams subjected to a series of concentrated loadings or having segments with different moments of inertia. Consider the beams shown for the development of the two theorems. The simply supported beam with uniform loading. If we draw the moment diagram for the beam and then divide it by the flexural rigidity EI, the M over EI diagram is developed as shown. What we did before is we draw the shear diagram, then after that the moment diagram. For this particular theorem, the difference is that there is the divisor EI. We need to include this one, especially if we have different values of EI for every segment. If we take a differential element of the M over EI diagram, that is with a width dx, and take the angle between them, the angle theta between them is equal to M over EI times dx. So here the change in d theta is in the slope of the tangents on either side of the element dx is equal to the lighter shaded area under the M over EI diagram. So take note, this equation was actually derived in the elastic beam theory. So this is quite useful in determining the slope of the tangents, as you can see in the elastic curve. If we integrate this equation from point A on the elastic curve to point B, we can have theta B over A is equal to the integral of M over EI dx. Here the minimum limit is A and the maximum limit is B. And there is a subscript on the angle theta, that is B with respect to A. What does it mean? We are taking the angle of tangent from the tangent at point B with respect to a tangent at point A. To visualize this one, you can look at the elastic curve on the right hand side of the diagram. If this is point A and if you draw a tangent line there, this is the tangent at A and this is point B. Drawing a tangent line here will give us tangent B. The angle between these two tangents is defined as theta B with respect to A. So if you say theta B with respect to A, we measure the angle between the two tangents. This equation actually forms the basis of the first moment area theorem. Theorem 1 states that the change in slope between any 2 points on the elastic curve equals the area of the M over EI diagram between these 2 points. So if you are interested on the slope between 2 points on the elastic curve, so it's quite easy to determine. Just draw the moment diagram divided by EI. So you have drawn the M over EI diagram. Then take the area of this M over EI diagram between point E and point B. That area will become, or that is the change in slope between the 2 points A and B. Also, the notation theta B with respect to A is referred to as the angle of the tangent at B measured with respect to the tangent at A. So this is what I am saying earlier. The angle theta B with respect to A is measured counterclockwise from tangent A. So you have to measure it from the tangent A. Counterclockwise from tangent A to tangent B. This is positive if the M over EI is positive. What will happen if M over EI is negative? This will be drawn on the compression side. So of course, if you have to draw that one, then this elastic curve will bend upward. So it's concave downward. So the tangent at point A will be going up. So that would be the case if the area is negative, then it is below the x-axis. The angle theta b with respect to A can be measured clockwise from tangent A to tangent B, and that would become negative. Note from equation above, the unit of theta B with respect to A is in regions. The second moment area theorem is based on the relative deviations of tangents to the elastic curve. So in this theorem, it's very important that you will be able to quantitatively or qualitatively draw the elastic curve, and this is what we have done before. I want you to develop your skill in drawing the qualitative deflection or elastic curve of the beam, because this is very important in the second moment area theorem, because we will be dealing with the relative deviations of tangents. So here the diagram, it is greatly exaggerated, of course, because in the elastic beam theory, we assume that the deflection is very small. So actually, it's difficult to see that one, but for discussion, it would be good if we can just exaggerate the diagram. So here, the exaggerated view of the vertical division, that is dt of the differential element dx. Here, if you draw the tangent line at the right side of the x, this is the tangent line, and another tangent line at the left side of the x, this one. The vertical distance between these two tangents is what we call the vertical division d sub t. This division is measured along a vertical line passing through point A, this one. So from this portion going to point A. Since the slope of the elastic curve is its deflection are assumed to be very small, it is satisfactory to approximate the length of its tangent line by x. So this is our approximation, because the deflection is assumed to be very small. So if we assume that this distance is x, then also this distance will be equal to x, and so this one, so that the arc ds is also equal to dt. If we use the circular arc formula, that is, if you remember a circle, the arc s is simply equal to the angle theta times the radius r. So in this case, we can just look at s as dt. The angle is this portion, d theta, and the radius is equal to this radius. But since this slope is very small, we can just consider it to be equal to x. So that dt is equal to x d theta. So that's the main reason why we can able to compute dt as a function of x and d theta. Again, you have to remember the deflection is assumed to be very small. So here, if we have to use the equation d theta is equal to m over ei dx, the vertical division of the tangent at A with respect to the tangent at B can be found by integration. So in which case, the division, this one, with respect to division at point A with respect to B, if the tangent line is drawn at B, then this is the division from this point A to this point. This is the vertical line. If we have to compute, or if we have to use the circular arc formula, that is, the arc is equal to the interior angle times the radius, and since the deflection is very small, then the radius can be assumed to be equal to x, this one, x times the angle d theta, but d theta is actually equal to m over ei dx. That's why this equation is equal to t a over b is equal to this x times d theta, and d theta is m over ei dx. So the integral is taken from point A to point B. But if you recall from your statics that the centroid of an area is determined from the integral sign or equation x bar times the integral of dA, which is also equal to the integral x dA. And since the integral of m over ei dx represents an area of the m over ei diagram as we have derived in theorem 1, we can also write the division of A with respect to A equal to x bar, that is the centroid of the area, times the integral of m over ei dx from A to B. which is the area of the M over EI diagram between A and B. So I think this is the crucial part. If you don't really understand this one, it would be difficult for you to apply. But of course, don't worry. Even if you don't understand it now, it would be clearer if we have some examples. So here from this equation, the distance x bar from the vertical axis through A to the centroid of the area between A and B, as you can see in the diagram here, we have the M over EI diagram. Then this is the dot. The distance between this with respect to A is the centroid x bar. So from this equation, the secant moment area theorem can now be stated as follows. Theorem 2. The vertical deviation of the tangent of the point A on the elastic curve with respect to the tangent extended from another point B equals the moment of the area under the M over EI diagram between the 2 points A and B. This moment is computed about point A, the point of the elastic curve where the deviation TA with respect to B is to be determined. So here the notation of the deviation TA with respect to B, where the first subscript A represents the moment arm, or the moment arm should be measured from point A. So that would be your guide in determining the vertical deviation. If we have to say that the moment of the positive M over EI area, or if the moment M over EI area is positive from point A to point B, then it indicates that the tangent at point A is above the tangent to the curve extended from point B. So you can see it here in this diagram. Since similarly, negative M over EI areas indicate that the tangent at A is below the tangent extended from B. That is if the moment diagram is negative. So the curvature is concave downward. Here you have to take note that the tangential deviations of A with respect to B is not equal to the tangential deviation of B with respect to A. You can see here in the elastic curve in figure F, they are actually not the same. But of course, for special cases, especially for symmetrical beams and loadings, there would be a chance that these two deviations will be equal. But in general, they are not equal. The moment of the area under the M over EI diagram between points A and B is determined about point A to find tangential deviation of A with respect to B, or TAB for short. And it is determined about point B to find the tangential deviation of B with respect to A, or TBA. I hope you understand this one. This would be the crucial part in using the secant moment area theorem. As a warning, it is important to realize that the moment area theorems can only be used to determine the angles or deviations between the two tangents on the beam's elastic curve. As we have derived the theorem 1 and theorem 2, it's only about the angles and the vertical deviations. No deflection. In general, they do not give a direct solution for the slope or displacement at a point on the beam. But these unknowns must first be related to the angles or vertical deviations of the tangents at points on the elastic curve. Usually, the tangents at the supports are drawn in this regard since these points do not undergo displacements and or have zero slope. So it's very important to draw the tangents at points that do not undergo displacements, especially the supports. Specific cases for establishing these geometric relationships are given in the example problems. So we have here the procedure for analysis. The following procedure provides a method that may be used to determine the displacement and slope at a point on the elastic curve of a beam using the moment area theorems. For the M over EI diagram, determine the support reactions and draw the beam's M over EI diagram. You can use or you can draw it using the classical way, drawing the shear diagram first and then the moment diagram, then divided by EI. Or you can use also the method of superposition. The the cantilever beams with specific load cases. In that way, you can just choose any point on the beam as a fixed portion, and you can just draw the moment diagram of its external forces. In that way, it would be easier to compute the area of the moment diagram and the centroid. If the beam is loaded with concentrated forces, the M over EI diagram will consist of a series of straight line segments, and the areas under moments required for the moment area theorems will be relatively easy to compute. If the loading consists of a series of concentrated forces and distributed loads, it may be simpler to compute the required M over EI areas and their moments by drawing the M over EI diagram in parts using the method of superposition. So this is what I am saying earlier. You can draw the M over EI diagram in parts using the method of superposition as we have described before. In any cases, the M over EI diagram will consist of parabolic or perhaps higher order curves, and it is suggested that the table in the inside back cover of the book of HIBBELER to locate the area and the centroid under this its curve. I have taken the liberty of giving you these geometric properties of areas. Of course, I understand that you already have discussed this one in your statics of rigid bodies, but you need to review these geometric properties. For a triangle, that would be quite easy. A trapezoid, also easy. But for the parabolic spandrel, you have to take note the area should be 1/3 times the base times the height, and its centroid with respect to the longer the other side, the edge, is 1/4 of B. For the semi-segment or nth degree curve, you can use these formulas. For a semi-parabola, you can use A is equal to 2/3 B edge, and the X bar is 3/8 of the base B. For the spandrel of nth degree curve, you can use also this equation. So if it's a second degree curve, that's n is equal to 2, so 1/3 BH, that's parabolic spandrel. But if it has a degree n equal to 3, that would be 3 plus 1/4, so 1/4 BH. And the x bar is b over n plus 2. If n is 3, that's b over 5. Here, take note that the one of the slopes should be 0. You cannot just use this one if one of the slope is not 0. For the elastic curve, draw an exaggerated view of the beam's elastic curve. Recall, even though it is exaggerated at the supports, there should be no displacements, except if there will be a settlement as given. But normally, if it is not, then there will be no displacements. And you can just draw the elastic curve according to the moment diagram, if you can follow that one. A positive moment, concave upward, a negative moment, concave downward. Also recall that the points of zero slope occur at fixed supports, and zero displacements occur at all fixed pin and roller supports. If it becomes difficult to draw the general shape of the elastic curve, use the moment or M over EI diagram. Realize that when the beam is subjected to a positive moment, the beam bends concave upward, whereas negative moment bends the beam concave down. So this is what I am trying to say earlier. Furthermore, an inflection point or change in curvature occurs where the moment in the beam or M over EI is 0. The displacement and slope to be determined should be indicated on the curve. It's very important. If you draw the free-body diagram, you can just directly draw this one. Since the moment area theorems apply only between two tangents, attention should be given as to which tangents should be constructed so that the angles or divisions between them will lead to the solution of the problem. In this regard, the tangents at the points of a non-slope and displacements and at the supports should be considered, since the beam usually has zero displacement and or zero slope at the supports. For the moment area theorems, you can apply theorem 1 to determine the angle between two tangents, and the theorem 2 to determine vertical deviations between these tangents. Realize that theorem 2 in general will not yield the displacement of a point on the elastic curve. Of course, it's in general, but there are cases that this will yield the elastic curve, especially for cantilever beams. When applied properly, it will only give the vertical distance or the deviation of a tangent at point A on the elastic curve from the tangent at B. After applying either theorem 1 or theorem 2, the algebraic sum or sign of the answer can be verified from the angle or deviation as indicated on the elastic curve. Here is an example taken from HIBBELER, a cantilever beam loaded with 2 kips at the pre-end, that is at point C. We would like to determine the slope at points B, 15 feet from support A, and C, the pre-end, 30 feet from the support. Take that A is equal to 29,000 psi and I is 600 n's to the power 4. First, you have to draw or compute the reactions. But here, since this is a cantilever beam, the reactions is just very easy. So you can just directly draw the M over EI diagram. Actually, if you only use the method of superposition, since this is cantilever, you don't need to compute the reaction at point A. If you consider point A as your fixed portion of the method of superposition, we only have one force left. Again, if you choose A as the fixed end for the method of superposition, we only have the force remaining 2K downward. So for a cantilever beam with a concentrated load at the end, it will give us a triangular moment which is negative. So here is the moment diagram divided by EI, since the EI for the span is constant, so it's quite easy to draw the M over EI. That is equal to 2 times 30, that's minus 60 over EI. At point B, since B is 15 feet from point A, which is half of the cantilever, so M over EI at that point is just simply equal to minus 30 over EI. For the elastic curve, since it's a cantilever loaded with a vertical loading, so your curve or your cantilever beam should bend downward. That's is concave downward. So here the 2 kilonewton load causes the beam to deflect in downward. Here the elastic curve is concave down. The tangent at A, that is at support, is always horizontal because it's a fixed support, so there will be no rotation. So if you have to draw a tangent line at A with respect to the elastic curve, then this tangent line at A will just follow the original position of the beam, that is horizontal. The tangents at B and C are also indicated. So with respect to the horizontal, if you draw the tangent at point B, you can see here the tangent line, and the angle of rotation at point B is simply equal to the horizontal line and the tangent line at B, that's theta B. But with respect to the tangent A, tangent B and tangent A, the intersection angle is equal to theta B with respect to A. If you draw the tangent line at point C here, again at the pre-end, you will get the angle theta, theta C at this point. That is from the horizontal to the tangent line at point C. But if you have to continue this tangent line at C towards tangent A, the angle between them is the theta of C with respect to A. Here, we are required to find the angle theta B and theta C. So by the construction, the angle between tangent A and tangent B, that is theta B over A, is equivalent to theta B. How is that? Look at this diagram by just using geometry, since this is tangent is horizontal. Also, this line from B is also horizontal. And we have the tangent line at point B, which is transversal line to the parallel line. So if this is angle theta B, and this is theta B with respect to A, then this should be the same according to the trigonometry or geometry. So theta B is simply equal to theta B over A. And so with the angle theta C is equal to theta C over A because of the geometry diagram. So here you cannot just directly compute theta B and theta C, but instead take the theta of the tangent from point B with respect to A. That is the moment or the area of the M over EI between A and B, this darker shaded portion. But for theta C, which is equal to theta with respect to theta at tangent at C with respect to A, that's C to A. So meaning you have to take the whole M over EI diagram. This area of this is equal to theta C. So you can see here. So here the theta B with respect to A, I am trying to say the area of M over EI diagram between A and B. So this darker shaded portion, as you can see, this is composed of, or this is actually a trapezoid, but we discussed last time that trapezoid is quite difficult sometimes, but it's easier if we can only divide this into simpler diagrams, just like rectangle. So 15 by 30, and then in triangle, that's 60 minus 30 or 30 by 15. So as you can see, the area of the rectangle is minus 30 over EI times 15 feet. So this one. Take note the unit of 30 over EI is skip times 15 minus this triangle. This is negative, so that's why it's minus. Minus 1/2 of the triangle, 60 minus 30 times the base 15. So you can just compute this one, and the result is minus 675 kPa per EI. So we have determined the angle theta B through this theorem 1. Also, you can substitute the numerical value for E and I so that you can find the value of theta B. Take note, you need to convert it to inches. This should be compatible. So that theta B should be in regions. So here the answer is minus 0.00559. That is the moment is negative, or the tangent line is above the elastic curve. So it's clockwise direction. The other one is theta C. Theta C is equal to theta C with respect to A. So the whole moment or M over EI diagram, the area of this should be equal to theta C, or that is theta C with respect to A, which is equal to a triangle 1/2 of the height minus 60 over EI times the length 30 feet. So here theta C is minus 900 kPa square over EI. Again, substituting the numerical values for the flexural rigidity EI, you can compute for theta C, that's negative 0.00745 regions. Another example, a cantilever beam, but here take note that the moment of inertia of segment AB is twice the moment of inertia of segment BC. Again, this is very useful for this particular problem. The moment area theorem is simple to apply here. So we would like to determine the deflection at 2 points, B and C of the beam. We can take the values of the moment of inertia of its segments as indicated, and take E is 200 gigapascal. 200 gigapascal is actually the modulus of elasticity of the steel. As you can see, we are using a wide flange. Again, you can compute for the reaction if you want, but since this is a cantilever beam, it's not necessary. You can just choose the fixed end or point A as the fixed end portion using the method of superposition. Here we only have one couple that is 500 Newton meter with no other loading. So you don't need to compute for the reaction for this particular beam. You can directly construct the M over EI with respect to the 500 Newton meter. Again, take note that the moment of inertia of segment AB is twice the moment of inertia of segment BC. So you can just use that one to simplify the M over EI diagram. So here we have initially it should be 500 over EI, but since the segment AB has twice the moment of inertia with respect to BC, then you can just divide this by 2. So instead of 500 divided by 2, the moment or M over EI is 250 over EI or BC. So here is the M over EI diagram. And to determine the deflection, you need to draw first the elastic curve. And since the couple M will tend to bend the cantilever beam upward, then the deflection should be positive. And again, since this is a fixed ended portion, if you draw a tangent line at point A, your tangent line at A is horizontal. And draw the tangent line at point B, and if you connect it with tangent A, you will be able to determine the angle theta. Or here, you can just directly determine the tangential division of point B with respect to a tangent drawn at A. So that's TB over A. Also at point C, if you draw a tangent line at point C, the distance between point C with respect to the tangent line drawn from A is equal to the deflection delta C, or the tangential division of point C with respect to the tangent drawn at A. Again, this is only the special case that you can just directly use Turing to compute for the deflection, because this is a cantilever. But for other beams, you cannot just directly use this one. So here, the angle or the deformation delta B is simply equal to the tangential division of B with respect to a tangent drawn at A, and delta C is simply equal to the tangential division of point C with respect to the tangent drawn at A. And for the tangential division, you just have to take the area moment of the M over EI from point A to B. And then for this TCA, just take area moment of the M over EI with respect to the segments A, C. It's just quite easy, okay? So this is just A to B. So we have a rectangular M over EI diagram. So that's 250 Newton meter. Again, the unit here is Newton meter divided by AIBC times 4 meters, the length of the rectangle. So that is equal to 2000 Newton meter cube per AIBC. And if you substitute the numerical data, it will yield 2.5 millimeter. And in calculating for the deflection, again, you really have to be to take care about the units. It's very important that the units will be an, or it should be compatible. For delta C, that is the tangential division of C with respect to A, you have to consider the whole M over EI diagram. So here we have the smaller triangle, rectangle, and the larger triangle, rectangle. So that's 250 times the length 4 times the moment arm taken from C. The centroid of this triangle, or rectangle I mean, is 2 meters from point B plus the distance 3 meters from point C to B. So that is why 3 plus 2, that's 5 meters, plus the 500 over EIEC times the length 3 meters times the moment arm with respect to C, that's 1 half of 3 or 1.5 meter. And calculate for delta C by substituting the values of E and I. So here delta C is equal to 9.06 millimeter. This should be greater than the deflection at point B, because at point C that is a pre-end. Delta B is 2.5 millimeter and delta C is 9.06 millimeter. Since both answers are positive, they indicate that points B and C lie above the tangent at A. Otherwise, it should be negative if it is going down. We have another example, a simply supported beam with a load at the center, 20 kilonewton. we would like to determine the slope at point C, that is at 1/4 point of the beam. Assuming E is 200 gigapascal and I is 6 times 10 to the power 6 millimeter to the fourth. Take note the moment of inertia has a unit of millimeter to the fourth or hands to the fourth. Here, you can just compute the reactions first because this is a simply supported beam and symmetrical. So just divide 20 kilonewton by 2. So the reaction at point A is 20 kilonewton up and the reaction at B is 10 kilonewton up. So there should be the same reaction, 10 kilonewton up for A and B. So assuming that we have to use the method of superposition, take the fixed portion at point D so that we can just directly draw the moment diagram due to the reaction at A and the reaction at B. So this is the result. 5 or 10 kilonewton times 6, so that's 60 kilonewton meter over EI. So this one. So this is the M over EI diagram. And then you can just draw the elastic curve since it's a simple beam loaded with gravity load downward. So the simple beam will bend downward or concave upward. Since the loading is applied symmetrically to the beam, the elastic curve is also symmetric. We are required to find theta C. So here, if we are required to find theta C, just draw the elastic curve and then draw a horizontal line at point C and then draw the tangent line. The angle between the tangent line at C and the horizontal line at point C is equal to theta C. And how do we determine this one? Also remember that at point D, since it's symmetrical, at point D, this is at the middle, the slope here is equal to 0. Remember, it's symmetrical. So the slope should be equal to 0 at the maximum deflection. So you can just draw the tangent line at point D. In this case, it's also horizontal. So the angle between the horizontal line at point D and the tangent line with respect to C is equal to theta D over C, or the angle theta of point D with respect to C. Again, using geometry, you can just say that theta D over C is simply equal to theta C. So to solve for theta C, just compute the area of M over EI between C and D. That's why theta C is equal to theta D with respect to a tangent drawn at C. So here we can just directly determine the area between C and D. Again, we have a trapezoidal loading. It's easier if you just distribute it or divide it into rectangle and triangle. For the rectangle, we have 30 over EI, the height, times the width, 3 meters, plus the triangle, 1/2 of the distance or base, 3 meters, times the height, 60 minus 30. Then theta C is 135 kilonewton meter, since we have multiplied it with another meter over EI. Thus, theta C, by applying the values of E and I, is equal to 0.112 radians. We have the same beam or a different beam, a simply supported beam, but with the couple applied at support A. What would be the deflection at point C for this particular beam? Again, you can just draw the M over EI diagram, either by computing the reaction first, because here we have a couple and we have two reactions at point A and point B, so it's important that you will be able to compute the reaction at A and B. If you take moment at point A, that's 5 kPa divided by 24, so that would be 5 over 24, or simply on the other side, also 5 over 24 up. It depends on you on what particular portion that you will assume as fixed. If you use the method of superposition, since the reaction at point B is 5 over 24 upward, then I can just use the reaction. So for the M over EI diagram, the concentrated load will form a triangular moment, then simply divided by EI. So the 5 over 24 times 24 will result to 5, then divided by EI. So the moment M over EI diagram is a triangle with height 5 over EI. So in this particular beam, what we are looking into is the deflection at the midpoint, that is at point C. So we expect that if we draw the tangent line at point C, uh, take note, we do not expect that the maximum deflection will be here because the loading is not symmetrical. So we will just assume that the deflection at point C is equal to delta C, this one, from the original horizontal line to the elastic curve at point C. That's delta C. That's what we are looking for. But if you use Theorem 2, we cannot just directly compute that one. If you draw the tangent line at point C, then we can just draw the vertical division at point C with respect to a tangent drawn at point B. Again, at support, if you draw the tangent line, there will be no displacement at the support. Just draw the tangent line and it will go in that direction. So in this case, we cannot just directly compute delta C, even though we can compute for the tangential division of point C with respect to tangent at B. What shall we do? If you look at this triangle, you will see that this vertical distance, this vertical deviation, is actually the deviation of point A with respect to a tangent drawn at B. And this triangle has a length of 24. So with this other triangle, it has a height of delta C plus TC over B with the base of 12B. The only unknown is delta C. By computing TC with respect to B and TA with respect to B, by ratio and proportion, we can compute for delta C. By ratio and proportion, delta C plus TCB is to 12 is equal to TA over B is to 24. So that would become 1/2 of TB, or delta C is equal to 1/2 of TB minus TCB, this equation. So we need only to determine the tangential division of A with respect to B and tangential division of C with respect to B using the M over EI diagram. Take the moment for TA with respect to B, so the whole M over EI diagram, then times this centroid with respect to A, that's 1/3 of 24. So here would be the details. 1/3 of 24, that's the centroid, times the area 1/2 of the height 5 over EI, times the base 24. So it will give us 480 kPa cube over EI. And if you take the tangential division of C with respect to a tangent drawn at B, then we need only to consider this smaller triangle with the height of, since this is at the middle, 5 over 2, that's 2.5 over EI. And the moment should be taken from point C. So that's the centroid of this triangle is 1/3 of 12. So 1/3 of 12 times 1/2 times 2.5 over EI times 12. So the result is this one, 60 kPa cube over EI. If we substitute this in the equations that we have derived using ratio and proportion, we can compute for delta C. That's 180 kPa cube over EI. Take note again with the working units in kips and inches, and substituting the values of E and I, you will be able to compute for delta C. That's 0.511. And so this is the point that I'm telling earlier, that in general you cannot just directly compute the deflection using the moment area theory. You have to look into the geometry of the elastic curve. So that's why it's very important that you will be able to master the skill in drawing the qualitative elastic curve of the beam, so that when you draw the tangent lines, it would be easier to see the relationships between the deviations and the angles. Of course, I will give you the other or the remaining examples to look into. I think it's quite self-explanatory. It's quite simple, and you can just follow the diagram and use the geometry again. In this case, the tangent at A is just above the elastic curve, and you can also take ratio and proportion to compute for the displacement at the endpoint. Endpoint? Yeah, the deflection at the endpoint, point C. Okay, so you can just follow these slides and you can compute for the delta C. I think that's all for the moment area theorems, and it's very important that you have to remember that one. But this is very useful for simple beams. For complicated beams, it would be difficult to find the deflection and the slope. But of course, it's quite important if we will be able to compute the slope and deflections of simple beams with simple load. That's all for today. Thank you for listening.